Yes, Molly, why don't you go sit next to,
Foreman?
yeah, Bormit's fine. Mark, you're okay, you're not in there.
Wait, why is there
Mark's a little bit in there, his arm.
As long as you don't get his face.
We could move through it. Okay, we had a little bit more science in the news. Yes, Jessica. That's the first time I called you Jessica. Okay, Aaron.
Is that a point?
No.
There's a plan, or at least a proposal of a plan near Vancouver to make a place for oil barges to go through, except they'd have to like cut away part of this one really big forest called the Great Bear Forest.
Oh
And
no.
so it's threatening like 3 different species of whales and a whole bunch of other natural things, and it's gonna upset the balance, and people are fighting it. And it's apparently gonna be like not a literal war, but it's gonna be an issue.
Yeah, that would be, it's always kind of tough balancing the development versus the need for new resources. The other big, fight too is, are you going to build a pipeline from the Canadian oil down to Texas? Like, I think I mentioned this to you before, they want to build a pipeline to get the Canadian oil, it's called shale oil, and the pipeline would go through North Dakota, South Dakota, Nebraska, Kansas, Oklahoma, all the way down to Texas.
Huge.
Granted, my solution was to build a refinery up in Duluth Superior, keep all that money here, but that again, that would probably be a problem. So that's just my thought. Totally crazy thought maybe. Yep, Joseph.
This isn't really science, but like, is it true that they're trying to get rid of dollar bills and make them like coins?
I
I
don't know.
heard they were getting rid of like.
But I think someone else had some science in the news before we.
I do.
Yep, Monroe.
Um,
I don't want to get too far off topic.
so I found an article that talks about like, so these researchers were like studying mice and like how they age, and they found this like type of cell that like the mice that are like cleansed of this cell like don't age as fast, and so like if you get rid of that cell, like
Is it a type of cell or is it the length of the chromosome?
it's like senescent cells. Is what they're
Okay,
called.
senescent cells. Okay,
Yeah.
so it is a type of cell.
Yes.
What do those cells do to make you age?
The mice who were like cleansed of those didn't develop cataracts and avoided the usual wasting of muscle and can like exercise for longer.
But do they know what those cells do to cause that, or no? Or they just notice that these cells, when they're gone, you don't get those
I think,
cells?
yeah, they don't quite know what they do because they just recently like, they didn't know if they were like good or bad or like what they did, but this study like showed what they actually do.
So I guess just the first step is these cells must do something, they don't know what, but if you have a lot of them, you tend to age a little bit faster. Interesting. Okay, so, we're going to finish our discussion about the mole today, and it gets a little bit tricky. Now yesterday, we talked about Avogadro doing experiments with gases. Alex, is this clear? I mean, is it like large enough or no?
And if I get it large enough, then it'll, if I get it to where you can read it very well, then it'll cut out like.
Right, I know. So you have to balance going in and out.
All right, that's good.
So yesterday we wrote this on the board, right, Jordan?
Yep.
So Carrie, one thing we noticed, or at least Avogadro noticed, is that if you took same amount of gas for hydrogen, nitrogen, and oxygen, the same ratio kept appearing. That if you took 5 liters of hydrogen, nitrogen, and oxygen, the ratio of their weights was 1 to 14 to 16. If you took 10 liters of those gases, the ratio was still the same, 1 to 14 to 16. If you took 25 liters of those gases, the ratio of their masses were still the same, 1 to 14 to 16. So as long as you have the same volume of all of those gases, you get the same ratio of gas, 1 to 14 to 16. Now we took 5, 10, and 25 liters. What if we went smaller? What if we went with a balloon, Ryan, so small that only one atom of the gas could fit in the balloon? What would the ratio of the weights be?
The same.
the same, 1 to 14 to 16. So if in theory we could have a balloon small enough that we could only fit one of those atoms in there, the ratio of the weights would still be the same, 1 to 14 to 16. And so we use that to begin to build our periodic table of elements. Which one is the lightest out of the three? Hydrogen. So we will pick hydrogen then as our standard. Just like when we were doing that example of building a periodic table of students. We said, okay, we're going to build a periodic table. So we're going to start with the lightest student, and we're going to be the weight of 1 Barton. Right? Let's pick on you. Who did I pick on yesterday?
I don't think you talked about that in our
Oh,
class.
okay, let's build a periodic table of students then.
Okay.
So if we're going to build a periodic table of students, just like hydrogen is the lightest, we got to pick the lightest student. So I'm going to pick on you, Allison, just because you're a nice person. So Allison weighs 1 Barton. Okay? And then we measure everything off of her. So Ryan weighs 3 Bartons. Max weighs 5.5 Bartons. And I weigh 12.8 Bartons. Okay? Now, do we know what a Barton is? No. But we do have a nice ratio, like this. Allison is 1 Barton. Ryan is 3. Max is 5.5. I'm 12.8. So it's helpful in that we have a ratio, but it's not helpful in that we don't know what a Barton is. So kind of the same thing they did with the periodic table. They took the lightest one, hydrogen, and they said 1 atom of hydrogen will weigh 1 atomic mass unit. Okay? So we don't know what an atomic mass unit is, but hydrogen is going to weigh 1 of them. Just like we don't know what a Barton is, but Allison weighs 1 of them. We can abbreviate atomic mass unit with the letters AMU. And if writing the letters AMU gets too much Alish, you can abbreviate AMU with the letter mu, the Greek letter mu, right? You're familiar with mu? You take Greek. That is the Greek letter mu. 2 tails, 1 in the front, 1 in the back. So you can abbreviate atomic mass unit with AMU, or you can abbreviate it with mu.
Isn't that like the thing from?
Micro, yeah, it's also the Greek micro. So any questions so far? All right. We're going to make another table then. So if 1 atom of hydrogen weighs 1 AMU, what would 1 atom of nitrogen weigh? 14. I'm just going to use the. And what would oxygen weigh? 16. So there are our ratios. Again, we don't know what an AMU actually is. It'd be nice if we did, if we knew what it was in grams or kilograms. Yep.
Why are all the numbers on there like decimal form?
Well, we'll get there. The reason why there are decimals up there is because there are isotopes.
Even like your oxygen and marine nitrogen.
Yep, every element up there has isotopes, and so you end up with not exact numbers. But right now, in 1800, according to Dalton's theory, all atoms of an element are all identical. So in his world, there are no isotopes. What if I took 10 atoms of hydrogen? What would 10 atoms of hydrogen weigh, Melissa? 10 AMUs. How about 10 atoms of nitrogen, Carrie?
Oh. Yeah, 104.
How about 10 atoms of oxygen, Fletch? All right. So, the ratio is still the same, right? 1 to 14 to 16. So even though I got 10 atoms of it, we still end up with the same ratio. What if we have 1,000 atoms of hydrogen? How much would that weigh, Mark?
1,000 M's.
How about nitrogen?
1,400. And 16,000.
The ratio is still the same, right? So like I said, we don't actually know what the AMU is. It'd be nice if we did. Just like we don't know what a Barton is. It'd be nice if we could take Allison, weigh her, find out what she weighs in kilograms, and then we would know what a Barton is. It'd be nice if we could take a hydrogen atom and weigh it. Because if we could weigh a hydrogen atom, then we would know what the weight of an AMU was. But can you take a single hydrogen atom, Kim, and mass it? No. How about 10 atoms? Can you take 10 hydrogen atoms and mass that, and then just divide it by 10? Nope, still impossible to get 10 atoms. Yep.
What's like the largest number you need in order to weigh?
Well, it's getting smaller, but 1,000 atoms? Could you weigh out 1,000 atoms? Still too difficult. Well, what about 1 gram of hydrogen? Could I weigh that out?
Yeah.
Okay.
So why do we put it in something that we don't know what it is? Why can't we put it
Well, because you can't weigh a single atom. If we could weigh a single hydrogen atom, we could just put it on the balance and boom, we'd be done. So basically, we start with a relative scale and say, okay, hydrogen's the lightest, we're going to assign a hydrogen a weight of 1. But a unit is made up. It doesn't relate to anything in the real, everyday world. So, if I weigh 1 gram of hydrogen, 1,000 atoms, 1,000 AMU, 14,000 AMU, 16,000 AMUs. The masses are different, but they all have the same number of atoms. I'm going to say that again slowly. They have different masses, but they all have the same number of atoms. So if I didn't write that number up there, could you figure out what number went there? You divide it by 1,000. I'm sorry, you multiply by 1,000. So what would have an equal number of atoms for the nitrogen? So 1,000 AMUs, 14,000 AMUs, 16,000 AMUs, all have the same number of atoms, 1,000. Same ratio, 1, 14 to 16. These three numbers should all have the same number of atoms. As long as you have the same ratio, those three things should have the same number of atoms. So now the question becomes, how many atoms is this? How many atoms are in 1 gram of hydrogen? How many atoms are in 14 grams of hydrogen? How many atoms are in 16 grams of oxygen? So how do you count atoms? They're very tiny, you can't go 1, 2, 3. So you have to try to estimate. Okay, Max, you ever go into a candy store and you see that big ball of gumballs? And if you can guess the right number, they give you the whole gumball machine?
Say I've never done that.
Oh, that's too bad. I feel bad for you, your poor childhood. So you can't count every gumball in the machine, you can't count every atom, but you can estimate. And this is one crude way of doing it. So you got your hydrogen, 1 gram of it. You have your hydrogen atoms in there. Shine light through it. If the light goes right through, there's nothing there. If it hits something, then there must be something there. So when you shine your light through, measure how much light gets diffracted. The more diffracting light, the more something must be in there. That's a very crude method of figuring out how many atoms are in 1 gram of hydrogen. Yep.
So like you just look at how much light was refracted and just say like, oh, that must mean that there's 2,000 atoms in this balloon.
More or less. I'm simplifying it big time.
But how do you even get that number?
So you can compare it to something that you do know how much is in there. Now, when you do this and you measure the amount of atoms in there, it comes out to be a very, very, very big number. 6.02 times 10 to the 23rd atoms. Yep.
But how do you like, how can you tell how many like debris are diffracting? Like, how do you?
Oh, you can measure the where the light hits on a piece of photographic film, or you could use sometimes when light is diffracted, it will change color. So you can measure what's called the light shift, like if it comes in as red light and comes out as blue light, you can measure how much. You can also have these things called luminosity, I can't remember the name. You can also measure how much light gets through. So I'm not giving you the exact detail, I'm just giving you kind of just the basic concept of how you could measure the number of atoms in here. Now, but here's one big problem though, Jenna. The three things we're looking at here are gases, right? Now, gas molecules are moving all over the place. So you're trying to count these atoms, but they're moving. It's kind of like trying to count cats. I mean, just moving all over the place gets really hard. So it would be a lot easier if we didn't work with gases. It would be a lot easier if we worked with a solid. And the solid they picked was carbon. And the ratio for carbon is 12. There are a couple reasons why they picked carbon. One, it's a solid. Two, it's relatively easy to get pure. So you can get, 12 grams of carbon, and you can be very confident that it's carbon and not a mixture of other junk. So if I have 12 grams of carbon, I have that many atoms. If I have 16 grams of oxygen, I have that many atoms. If I have 14 grams of nitrogen, I have that many atoms. And if I have 1 gram of hydrogen, I have that many atoms. Yep, sorry about
So
that.
they're just guessing on that number?
Not guessing, they're measuring. Okay? So if it's a measurement, it's not exact. This would have 3 significant figures. That is a measurement of the number of atoms in 1 gram of hydrogen, or 14 grams of nitrogen, 16 grams of oxygen, or 12 grams of carbon. And there are different ways you can measure the number of atoms in there. In fact, I think the most accurate measurement we have as of to date is, okay, the most accurate measurement we have to date is 6.0221367 times 10 to the 23rd. That would have 2, 4, 6, 8, 9 sig figs. So that's the most accurate measurement they have. Thank you. So, after you've said 6.02 times 10 to the 23rd a few thousand times, you begin to realize, let's have another name for it, because that's a mouthful. So they call it a mole.
Why did they call them?
A mole is Latin, as you know, Ms. Gabori, you're taking Latin. The mole is Latin for a pile or a heap. So if you want to heap of spaghetti for dinner tonight, just tell your parents, give me a mole of spaghetti. And they'll just heap it on there. Just throw a big old platter.
Will do.
I'm sure they'll know what you're talking about. Now, this is where I was saying that, you know, you don't have to quite understand everything about the theory behind the mole in order to use it. We're going to use this conversion a lot. It's a lot like using a dozen. There are 12 in a dozen, right, Ryan? Yeah. So if I have a dozen bananas, Brittany, how many is that? If I have a dozen rolls, how many is that? Okay, it doesn't matter. A dozen is always 12. If I have a mole of bananas, Jordan, how many bananas do I have? A mole of bananas, how many do I have?
Oh, 6.02 times 700.
Yep. If I have a mole of jelly beans, Ava, how many jelly beans do I have?
6.02 times 10 to the 23rd.
Right. So the only difference is this number is a measurement, so it's got 3 sig figs. It's not an exact number. We don't know exactly how much the mole is. It's a good measurement. Whereas we do know there's exactly 12 in a dozen. So the official definition of the mole is 6.02 times 10 to the 23rd particles in 12 grams of carbon. That is the official definition of the mole because, again, they picked carbon because it's a nice solid, you can get it pure. And now that we know how many atoms are in a mole, we can figure out how much one atom weighs. Because how much did one hydrogen atom weigh, Kim? 1 hydrogen atom weighs 1 gram. How much does 1 hydrogen atom weigh? 2 grams. No?
1 AMU.
1 AMU, right? So, if I have 1 gram of hydrogen, and how many atoms are in 1 gram of hydrogen? A mole's worth. If I take 1 gram of hydrogen and I divide it by that number, I get So one hydrogen atom would weigh 1.66 times 10 to the negative 24th grams. And if one hydrogen atom weighs that much in grams, and one hydrogen atom weighs 1 AMU, then that must be the mass of an AMU. We didn't, but now we do. When they figured out what the mole was, now we have a way to calculate it. We know that we weighed a gram of hydrogen. We know how many atoms are in a gram of hydrogen. So all I have to do is divide 1 by the number of atoms. So if you divide that by that, then I can calculate the actual mass of a hydrogen atom. One hydrogen atom weighs that much.
You're saying this still isn't all that accurate?
Yeah, I would say it's fairly accurate. I mean, it's not an exact number, but it's very accurate enough that it doesn't affect your calculations. But I mean, maybe someday, Max, you'll measure the mole out to another decimal point and everybody will throw you a party in your lab.
When you're actually doing the math, do you have, like, are you supposed to write out 6.02 to the times 10 to the 23rd? Do people just write, like,
It depends. Sometimes, usually they write a mole, 1 mole, because it gets to be a pain to write out 6.02 times 10 to the 23rd.
it's acceptable to do?
Yep. So now we have a couple important conversions. 1 AMU is that much in grams, and 1 mole is 6.02 times 10 to the 23rd. And so we will spend the next week or so using these 2 conversions a lot. So that means now it's time for homework.
Are we doing a lab?
Yeah.
We were gonna do a lab, and we are gonna do a lab, we're gonna push it back till tomorrow.
Oh.
Because I really think this problem is a lot of fun.
Love.
Because it really is a good thinking problem. You wanna talk about science reasoning? This is a good reasoning problem. Because it takes you back to the 1800s. It really makes you try to go through all the mental exercises that they did. What are you talking about? You guys are smarter than they were.
But clearly not. I did not invent.
Look, you guys are taking like pre-calculus and calculus. These guys didn't have it. You guys want to work computers and iPods.
Mole and an atom work.
Yes, but you know, but you guys know this stuff at age 16. These guys didn't know it until they're like in their 30s and 40s.
I would not have to know this stuff. It's different from them.
Okay, so we are going to do for homework number 2 and number 6.
That's what homework is, 2 and 6?
2 and 6. 6 is easy. 2, not so much.
Wait, so Joy.
Yep, just 2 and 6. 6, again, is easy. It's multiple choice. But 2 is hard, so we're going to do 2 together. And could you read number 2 for us? Okay. Ms. Sarbach.
You have gone back in time and are working with Dalton. He is working at a table of relative masses, and these are the data. These are his data. 0.602 grams of gas. A reacts with 0.295, is that what it says?
Yep.
Grams of gas B. 0.172 grams of gas B reacts with 0.401 grams of gas C. And 0.320 grams of gas A reacts with 0.374 grams of gas C. Assuming the simplest formulas, A times B, B times C, and A times C, construct a table of relative masses for delta.
Okay, so we're going to do part A first. So what we're doing is going to react element A and element B. Again, go back to the 1800s. They didn't know what some of these elements are. Dalton called hydrogen bi. He gave it his own name. So we are calling these two elements, elements A and elements B. Now when these two elements react together, what will the outcome be? AB. But what are the ratios? Would it be A1, B2 or A2, B3?
No?
How would we know? Well, they're telling us in the problem to assume the simplest ratio. Let's guess 1 to 1. Obviously, there's no way to know English when you're doing this, but they're saying guess. So how many grams of A do we have? 0.602, 0.295. If the ratio is 1 to 1, then we must be adding equal amounts of these two things, because we don't have any leftovers. So, which element is going to be lighter, the A or the B? B will be the lighter one. So if we're going to develop a table of relative masses, you look for the lightest element. Just like we look for the lightest student, look for the lightest element. Divided by its mass. And we end up with a ratio of 1 to 2. So in other words, B weighs 1, A would weigh 2B. So A is twice the weight of B. B weighs 1B, A would weigh twice as many B's. But there are not only 2 elements out there. There's more elements than that. And so they reacted B with C. And the mass of B is 0.172. And the mass of C is 0.401.
How can B be 2?
Because you have 2 different amounts of B. They're not telling us how much B there is, they're just telling us the mass. So again, we're assuming the ratio is 1 to 1. So we're assuming that we're adding equal amounts. So then which element must be lighter, B or C? B must be lighter. That equals 1. This equals 2.3. So that means C is 2.3 B's. So we've developed a relative table of masses. But we should double check our work and see what happens when we react B, or when we react A and C. Again, we'll assume simplest ratios. So if we assume simplest ratios, we've got 0.320 grams of A, and we have 0.374 grams of C. Now, who should be lighter? According to our prediction, A should be lighter than B. A should be lighter than C, right? Looking up here, is it? Yep. Now the ratio what is the ratio of C to A? The ratio of C to A is 2.3 to 2. So in other words, for every 1A, how many C should we have? So our ratio is 2.3 to 2, or you could say the ratio is 1.15 to 1. So hopefully this ratio up here is identical to this ratio. If it's not, we have a problem. So let's do it. N equals 1, divide that. And luckily, Kaz, the ratio is close enough. So we are pretty darn confident which one is the lightest element? B. Who's then the second heaviest? A, and then C. But the big problem with all of this, Carson, is we assumed everything was reacting in a 1-to-1 ratio, which is not, I mean, how do we know that? So that's where part B is a little bit more realistic. Now these guys in the 1800s, this is what they did starting off. They assumed the simplest ratio, and then they did some more experiments to figure out what was really happening. And so let's take a look at part B. Okay, Max, you want to read part B for us?
Write out the simplest balance equations and find the actual
No,
relative.
knowing some histories.
Oh, sorry. Knowing some history of chemistry, tell Dalton that if he finds the volumes of the gases at equal temperature and pressure, he need not assume the simplest formula. Collect the following data. 6 volumes gas A plus 1 volume gas B equals 4 volumes product. 1 volume gas B plus 4 volumes gas C equals 4 volumes product. 3 volumes gas A plus 2 volumes gas C equals 6 volumes product.
Okay, so we want to do the same thing as we did in part A. We want to develop a relative table of masses. But this time, we are not going to assume that it's a 1-to-1 ratio. Maybe it's 2 to 1. Maybe it's 2 to 3. So we're going to have to figure out the formula. Now, how are we going to figure out the formula? Well, we have more information. They tell us the volume of gases. And that gas A, and you do need to draw the pictures. You're not going to solve this without a picture, I guarantee it. So they say we have 6 volumes of gas A, and 1 volume of gas B, and it produces 4 volumes. Don't look very the same, do they? Okay, so this is our product, KB. We don't know what the ratio is. So Avogadro, this is why Avogadro was so important, said that equal volumes of gases have equal number of particles. Okay, he didn't say atoms or molecules, he said particles. So in other words, Kim, if I have 1 atom in this box, then I must have 1 in all of these boxes. 1 particle in all of them. If this happens to be a diatomic element, this is still one particle. It just so happens that they are attached. Two atoms, one particle. So if I have one particle in this box, I'd have to have one particle in all my boxes, okay? So let's just start off. We have element A. I've got one atom or one particle of element A in all my boxes. B. If there's one particle in each box, then how many particles have to be in each of these boxes? One. So, we have a problem. We already used up our B. So then, how do we get more of the AB? How do we get 4 volumes of AB if we already used up our atom? How about we chop it into fourths? So that means we have fourth there, fourth there, fourth there. So again, try to put your mind into them in the 1800s. It would make sense to say, okay, well, if we need 4 volumes, just chop that atom in fourths, and then we're good, except we still have a problem. We'd have 2 leftover A atoms. Where'd they go? As far as you know, you can't destroy mass. So, what does that leave us with? Problem. Well, Dalton assumed, hey, you know what? You can't destroy atoms. So Dalton said, I don't think this answer's right. That's why we write in pencil, I warned you. What if B was not monatomic? What if B was tetraatomic? That is still one particle. Yep, Carrie.
So why didn't the chopping it into corners work?
Because if you did that, your formula could be this. A1B.25. And again, Dalton's assumption was that you can't do that. Plus, there's still a problem with having 2 atoms left over that weren't used.
Oh.
So, the other idea would be that this thing is tetraatomic. You still have 1 particle, right? You each have 1 particle in the box. That's 1 particle, it counts as 1 because it's attached. So then I can do this. And that would be A1B1. But I still have a problem, right, Eilish? I'm still having 2 atoms not doing anything. Maybe this is not monatomic. Maybe A is diatomic. Now, it works out. There's 1 particle in each box. 1, 1, 1, 1. 1, 1, 1, 1. If you're attached together, you count as 1. What is the formula? A3, B1. And what is the mass of these 6 volumes of A? 0.602 grams. What is the mass of B? 0.295. So we're using the masses from part from part A. So now you can calculate, who did we say was the lightest element in part A? B. Is it still the lightest element? I don't think so, because we have what, 12 atoms of A? And we have only 4 atoms of B. I think A now is lighter. In 1 minute I can do it. Well, maybe I can't. Anyhow, for your homework, number 2 and number 6. Okay? You got a good start on number 2. It's tough.
I don't think I understand it. Alright.
How much sugar?